Okay, let's talk Bitcoin. We all know it's a revolutionary technology, right? But it has this famously dirty secret. It uses a staggering amount of energy. But what if the solution to crypto's biggest problem was hiding in the super weird, super complex world of quantum computing? All right, let's dive into this.
Just let that sink in for a second. We've got two massive challenges on our hands. One, making cryptocurrency sustainable. And two, finding something actually, useful for today's early-stage quantum computers to do. Well, a fascinating new paper suggests these two giant problems might just cancel each other out.
So first things first, let's really get a handle on the scale of this issue. We all hear that Bitcoin uses a lot of power, but how much is a lot?
Well, get this. The Bitcoin network's annual electricity use is greater than that of entire countries. Yeah, countries like Switzerland. All that energy is being burned by miners all over the world, running these powerful computers 24/7. But what are they actually doing?
They're doing something called proof of work. And honestly, it's a pretty brilliant system for keeping the network secure without anyone in charge. Think of it like a global lottery. You've got thousands of computers all guessing a random number at the exact same time. They're just burning through electricity, making trillions of guesses until one lucky machine stumbles onto the right answer. That's pretty much what Bitcoin mining is. It's incredibly secure, but it's also designed to be incredibly wasteful.
So, how on earth could quantum mechanics help with any of this? Well, some researchers came up with a new kind of proof of work, one that's specifically designed for a quantum computer. Now, before we get into it, just a quick reminder. A normal computer bit is like a light switch. It's either on or off, a 1 or a 0. Simple. A quantum bit, or a qubit, is more like a dimmer switch. It can be on, off, or exist in this weird mix of all the states in between, all at the same time. And that ability is what gives them their incredible potential power. Okay, with that in mind, to really get their idea, we need to clarify a super important term.
Okay, now what's really interesting here is this distinction. You've probably heard the term quantum supremacy. That's the huge, almost mythical goal of doing something a regular computer could never do, not in a billion years. But these researchers, they're focused on something much more down to earth, quantum advantage. That just means doing one specific thing better or faster than a classical computer. It's a way more achievable goal for the kind of noisy, imperfect quantum computers that we actually have right now.
And this quote just perfectly sums up their whole approach. They weren't looking for some impossible problem. They were looking for a Goldilocks problem, one that's really hard for our normal computers, but pretty straightforward for a quantum computer. And, this is key, consistent enough to be used in proof of work. That word deterministic is so important. It just means you get the same answer every single time you ask the same question. For a security system, that is an absolute must-have.
So here's the play-by-play of how their quantum proof of work would actually work. It starts off pretty much like normal Bitcoin mining. But then, right here at step 3, something really cool happens. That data gets turned into a set of instructions for a quantum computer. The quantum computer runs this little custom program and spits out an answer. That answer then gets hashed again. But the most crucial part is step 6. A totally normal computer can still check if the answer is right, super easily, and that's absolutely essential for keeping the whole network secure.
Okay, this all sounds pretty good on paper, right? But does it actually work in the real world? Well, they didn't just write a paper. They actually built it and tested it on a real-deal quantum computer.
They ran their quantum algorithm on a publicly available 4-qubit quantum processor from IBM. Now look, it's a small-scale experiment, for sure, but it is a vital proof of concept. And you know what? The results were really fascinating. First up, accuracy. Because today's quantum computers are, well, noisy, they make mistakes. The researchers found that the quantum computer's answer matched a perfect classical simulation about 69% of the time. Now that's not perfect, but it proves the system basically works. Any wrong answers just get thrown out. So what about speed?
And here is the twist. The 4-qubit quantum computer was actually 100 times slower at this task than a regular computer simulating the exact same thing. That's right, slower. So you're probably thinking, wait a minute, slower? Doesn't that mean the whole idea is a bust? Not at all, actually. See, the point of this first test wasn't to be faster. The point was to prove that you could build a simple blockchain secured by a quantum computer. And they did it. They successfully mined a chain of blocks. The real magic, the real advantage, that doesn't show up at just 4 qubits. It appears a little later on.
And this brings us to the most exciting part of their research, what they call the tipping point. This is where the projections into the future get really interesting, because it's all about how these different systems scale up.
So the whole game is right here on this chart. As you add more qubits to the problem, the difficulty for a classical computer to simulate it just explodes. It goes up exponentially. It gets impossibly hard, incredibly fast. But for the quantum computer itself, the difficulty only grows polynomially, which is way, way slower. Eventually, those two lines just have to cross.
To figure out where that crossover point is, the researchers defined quantum advantage for this task pretty simply. It's the speed ratio between the two computers multiplied by the accuracy of the quantum computer. This gives you a really good measure of useful speed because it takes into account those unavoidable quantum errors.
And this is the magic number they came up with. Based on their projections, a noisy quantum computer with around 30 qubits would hit what they call a minimal viable quantum advantage. At that exact point, you would officially become more efficient to use a real quantum computer for this kind of mining than to use a classical one. And here's the kicker. 30-qubit machines are totally within the realm of what we have today.
Now, if this were to happen, the implications are just enormous. All of a sudden, the billions of dollars being spent on traditional mining hardware could get funneled into quantum research and development. It would give these noisy early-stage quantum computers their first really big practical job. And of course, it could fundamentally slash the energy footprint of cryptocurrency.
So this leaves us with a pretty provocative thought. We could be standing on the verge of a brand new kind of tech race, not for faster graphics cards, but for more powerful and more accurate quantum processors. A race that could totally reshape the next era of both digital money and the very nature of how we compute.